This is the second mini lecture for section 13.2 of the textbook. Sorry, section 13.3 of the textbook. The relative frequency of an interval in a data set is the fraction of the population in that interval. For example, consider the data from slide 1 of section 2.1 or 13.1 of the textbook. Okay, so we had this on the first slide. 24 scores. You might think of these as representing test scores or something. And when we drew a histogram and a line graph of that data, we divided it up into 4 intervals. Okay, there's interval 1, 60 to 69, 2 was 70 to 79, 3 was 80 to 89, 4 was 90 to 99. Okay, and we use this to draw the histogram. Okay, when we talk about relative frequency, we don't care about the absolute amounts. What we care about is the percent of the population that is in that interval. So for example, for 60 to 69, there were 3 scores in all. Well, 3 out of 24 was in that interval. 3 out of 24 is 0.125, which is 12.5%. And similarly for the other intervals. So the relative frequency of interval 2 was 54.2%. Interval 3 is 25.0%. Interval 4, it was 8.3%. Okay, so here we're not talking about frequency, we're talking about relative frequency. We can illustrate relative frequency using a relative frequency histogram or polygon. Okay, so let's draw one of those. Instead of the vertical axis going up to represent the number of scores, it's going to represent the percent. So it should range from 0 to 1. The highest percent that I'm seeing is 54.2%. So we'll just make sure it goes up at least that high. I'm going to go by 5s. Okay, so we have interval 1, 2, 3, and 4. The picture I'm going to end up with here, it's going to look just like the picture we had for the ordinary histogram or line graph, but of course it's scaled differently. So let me lightly sketch the histogram and then I'll sketch the line graph a little more darkly. See, the first interval we have 12.5%. So that's going to be right around in here. I'm just kind of estimating. And then interval 2 is 54.2%. Interval 3 was 25%. It's 6 out of 24 of the individuals in our population. And then interval 4 is 8.3%. Okay, so that's our histogram, which I've just kind of lightly sketched. And I'll do the line graph on top of that more darkly. And remember, we just put a dot in the middle of the top of each bar and connect the dots. And then we can also put a dot to the left and right. And just connect the dots. And let's label the values here. Let's see, we have 0.125, 0.542, 0.250, and 0.083. So again, this is a relative frequency histogram. Now, if we think of each of these intervals as 1 unit wide, and we use the area formula for triangles or trapezoids or rectangles, and we add up the area underneath either the histogram or the line graph, what we'll get is 1. So the area underneath the graph adds up to 1, or we can think of that as 100%. Okay, the area under the graph represents the population. Okay, so that's a powerful idea. And this is a simple type of what's called a distribution curve, which is the subject of this mini lecture. If we imagine each interval in a relative frequency graph to have width 1, then the total area under the graph is 1, or 100%. Furthermore, the area between A and B is the fraction of the population between A and B. Okay, for example, suppose we have the line graph. Okay, I'll just make something up for the sake of drawing a picture. So the area underneath this relative frequency polygon is 1. But furthermore, if I take two values, they don't even have to be the endpoints of intervals. If I take, let's say, A and B, I look at the area underneath the graph between those two values. Okay, the area is going to be somewhere between 0 and 1. Because the area underneath the whole graph is 1. Okay, so this is going to be less than 1. And what we do is we interpret that as a percent. And that's going to be the approximate number of individuals whose score is between A and B. So again, the area between 0 and 1 represent the percent of scores between A and B. Now, in the study, as measurements are taken more and more closely, think, for example, instead of talking about grades on an exam, we're talking about heights to the nearest inch, or the nearest half inch, or quarter inch, or eighth of an inch. So as you make your measurements more and more closely, the graph becomes smoother and smoother. Okay, these little angle points get closer and closer together, and then so the graph kind of tends to smooth out. Okay, so you end up getting this smooth curve, but this smooth curve that you'd end up getting has the same property regarding area. So you might end up with something that is, for all intents and purposes, perfectly smooth. Okay, we have all been seeing curves like this lately because we're in the middle of the coronavirus pandemic. Okay, and they keep telling us, let's try to flatten the curve. Okay, that curve that they're talking about is a distribution curve. And if I take two values along the axis there, A and B, and I compute the area underneath the curve between those two values, then that area represents the fraction of the population within those two values. Okay, so same idea, even though we're talking about a smooth curve. And this might happen if your measurements are so precise that it's sort of like the intervals are so skinny that this just turns into a smooth curve. Or it could be that the population is just so large that for all intents and purposes it's smooth. So in the news, when you see those little curves for the coronavirus and how they're trying to flatten the curve, that's the case. The population is so large that you can approximate the number of cases day by day using a smooth curve. Now, a population with a normal distribution has a symmetrical bell-shaped graph. A normal distribution obeys the following rule. 68% of the population is within 1 standard deviation of the mean. 95% of the population is within 2 standard deviations of the mean. 99.7% of the population is within 3 standard deviations of the mean. Okay, so the normal distribution curve is this thing that you might have heard referred to as a bell curve. Okay, it's symmetric and has this bell shape. Okay, you can look in the textbook for more accurate portrayal of this. This picture I've drawn is supposed to be symmetric. Okay, the line of symmetry is the mean. That's right in the middle. So you have 50% of the data above the mean and 50% of the data below the mean. Okay, well, when we're talking about a large population with a normal distribution, we use this Greek letter mu. to represent the mean. Okay, and this rule tells us that 68% of the population is within one standard deviation of the mean. So if I take the mean and I subtract the standard deviation, which we represent using a sigma, that's the Greek letter sigma, which is the standard deviation of this large population. So I take that value. And then I also add the standard deviation to the mean. Then between these two values, you have 68% of the population. So if I were to compute the area in here, that would be 68% of the total area. But the total area is 1, or 100%. So between those two values, the area is 0.68. Okay, then 95% of the population is within 2 standard deviations of the mean. So that's mu minus 2 sigma, mu plus 2 sigma. Okay, so 95% of the data is within those two values. And then 99.7% is within 3 standard deviations. So this is very similar to what we were observing in the last section when we were computing the percent of the population within 1 or 2 or 3 standard deviations. Remember, in those examples, we saw that it was typically true that well over the majority was within 1 standard deviation, around 60 or 70%. And practically everything was within 3 standard deviations. Okay, that was for a small population, which was not a normally distributed population, of course. But in any population, you see approximately this. Okay, the 68, 95, 99.7 rule is the precise rule for a population with a normal distribution. For example, suppose a certain population with a normal distribution has mean 540 and standard deviation 60. Well, let's sketch the distribution curve again. It doesn't have to be really accurate. Okay, so the mean is 540. So here in the middle, we have 540. Standard deviation 60. So here we'll have 480. And 540 plus 60 is 600. So this tells me that 68% lies between 480 and 600. If I take 40 and subtract 60 again, I get 420. Add 60 to 600, I get 660. Therefore, 95% lies between 420 and 660. Okay, do the same thing again. We have 360 and 720. 99.7% lies between 360 and 720.